Hey everybody, I've got a joke for you. How many engineers does it take to change a light bulb? Well, none, because they're all out trying to invent the perfect light bulb. Right now there's thousands of engineers out there laughing hysterically. But if you're not, and you don't get it, then you better watch this show on engineering. Now, you could say there are two main things that a scientist does. They break things down to see how they work, and they build things up to see if they work. And as much as I love to break it down, today I'm in a building kind of a mood. I'm not sure what I'm going to build yet, what I'm going to use to build it. There's definitely some kind of building on the cards. Get it? They're cards. Doesn't matter. See, today's episode is all about engineering and the many and varied jobs that an engineer does. Check it out. Today on Scope, we find out how to make something tower into the sky, engineer a race car, and blast off with a little rocketry. Take a look around you. How many of the things that you can see do you think were invented or improved by engineers? Well, it's probably more than you realise, because despite their name, engineers don't only work on engines. Engineering involves a lot of building stuff, often to suit a very specific purpose or function. This means that a lot of their job is also inventing. Then, because they are inventing and building completely new things, they're usually the ones who have to operate and maintain their creations too. So the job of an engineer can be summed up into four main activities: design, construction, operation, and maintenance. And all this building and design requires an awful lot of science, namely physics, maths, and chemistry. And engineering is the practical application of all those formulas and calculations. So once you've decided exactly what you want designed and built, well, then you can work out exactly which engineers you'll need to speak to. If it's a road, bridge, tunnel, or building you need, then civil engineers can help you there. They design all the infrastructure of cities and towns and ensure that it's all safe and sound. But if it's a machine that you need, then call in the mechanical engineers. Destroy my robot! They build robots, engines, factory equipment, and other machines that do everything from pumping sewage to mixing dough. Aeronautical engineers deal with machines too, but specifically ones that fly. Planes and helicopters are all in a day's work, helping them take off and making sure they stay up there. And aerospace engineers deal with all the things that fly outside of Earth. They're the all-important rocket scientists. But none of these machines would have fuel if it weren't for chemical engineers. They're especially important in the oil industry, changing oil into other useful substances like petrol and plastic. They have to consider things like how dense or explosive different chemicals are and design different machine parts that will carry them safely. Of course, to get the oil in the first place, well, you'll need the services of a mining engineer. They work out how to get minerals from underground up to the surface and then design the equipment that will make it happen. Then they help design the process that will purify these minerals into a usable form. And then there are electrical engineers. They bring light and power to the world by designing wiring systems for buildings and machines. And electronics engineers deal with the more detailed wiring found inside electronic devices like computers, appliances, and robots. And as technology advances and problems become even more complicated, well, along come more engineers to fix them. For example, genetic engineering, which involves changing the genes of plants or animals. For example, to create sweeter pineapples or pest-resistant cotton. And they can also make cheap synthetic versions of things like drugs and vaccines. So pretty much everything you touch inside your house will have involved an engineer at some point during its design or construction. Maybe several engineers. In fact, any kind of designing or inventing could be thought of as engineering, which is exactly what Jules is up to right now, I think. I'm going to engineer this. Out.
Engineering is all about designing things to achieve certain goals. So with that in mind, today I'm going to see if I can improve on the good old egg carton to see if it can protect the eggs a little bit better. For this experiment, you will need some eggs, and the rest is limited only to what you can find around the house. You can try making an egg protecting contraption out of pretty much anything. I'm going to make 3 different structures that will hopefully protect the egg in 3 different ways. First up, I'm going to use padding. For my padding, I'm using soft, light objects that will leave plenty of space between them. So, when the egg is dropped, the bits of padding will squash together from the force of the collision. And so, the energy will go into squashing the padding and not squashing the egg. So hopefully the egg will stay intact. All right, well up next, I'm going to see if I can slow the fall of the egg. To do that, I'm making an egg parachute out of a plastic bag. Cut 4 pieces of string about 30 centimetres long and attach them to the bag, making sure they are evenly spaced around the opening. Then attach the parachute to a cup that the egg can sit in. Now this should make sure the egg will hit the ground at a much slower speed so it's less likely to break. And now for our last mission, spreading out the impact. And for that, I've got a huge foam ball that's been cut in half. The egg is going to sit inside the ball, so cut a hole about the same size and shape as the egg. If the egg rattles inside the ball, you might need to add some cotton wool to fill the space. Right, well I've got 3 egg protecting devices done. Now it's time to find a hard surface to drop them on. And of course, every experiment needs a control. So this is going to be our test egg with no structure protecting it at all. Cool, well let's see how we did. Well, the control egg, obviously that broke. But what about our structures? Well, let's have a look at the padding. Well, it wasn't too successful, but I think next time we should use a bigger container with more padding. That might do the trick. This structure was built on the same principle as the crumple zone in a car. All the energy of the crash goes into deforming the metal, and so the people inside stay safe. But for this test structure, unfortunately, the egg did not. Next, the parachute. Now that was supposed to work just like a skydiver's parachute and slow the fall of the egg. Now it slowed it down, but not enough to stop it from cracking. Okay, well let's have a look at the foam ball. The foam ball worked because it spread the force of impact over a greater area. Instead of all the force hitting the egg's shell in one spot, it hit the foam and spread evenly over the surface of the ball. This is why helmets protect you when you fall off your bike. Well, one structure worked out of 3, which isn't too bad, but I still think an egg carton is the best way to keep your eggs. Well, I think it's time for me to clean up. I think it's omelettes for lunch for me.
Huh. Well, that's a pretty odd way to make an omelette. Did look like fun, though. Although coming up, we're more interested in cracking lap times than eggs. So stay tuned for that. There. Did you know that the first kind of engineers were actually military engineers? They developed and built machines of war, catapults, that sort of thing. But then along came an engineer that worked on more peaceful projects, like building cities. And they were called civil engineers.
Towering skyscrapers, enormous bridges, cavernous road tunnels. These amazing feats of construction seem to defy the laws of physics by holding up millions of kilograms of weight for hundreds of years. But it's actually our understanding of physics and maths that make these constructions possible. Hi, my name's Brendan and I'm a civil engineer, which makes me an expert on how to keep structures standing. Just about every construction job you've ever come across would have involved some type of civil engineering. Engineers working on these projects use maths and science to figure out how we can build large and complex structures without them falling apart. But how exactly do engineers do this? Well, the process starts well before a construction worker has set foot on the building site. Architects and designers start the ball rolling by drawing up plans that outline the basic idea for the new construction. The engineers then use these plans to start designing each of the building elements in a safe and structurally sound way. They need to take many factors into account, including cost of materials and the impact of the structure on the environment. But perhaps the most important part is working out what forces will act on the building. Gravity, wind and soil movement are just a few of the forces which constantly push and pull different parts of a structure. Engineers calculate the magnitude of these forces using equations, calculators and computer programs. With a massive new building like this one, gravity has a big influence. Gravity is pulling this huge mass downwards, and without proper foundations, the building might sink into the ground. To get the foundation design right, engineers take into account the soil and rock conditions below the site, as well as the slope of the ground. Once we've designed and built a stable base for the building, it's onwards and upwards. To gain height in a building design, we use a combination of beams and columns connected together over numerous levels. These elements work together to transfer all the weight from up the top of the building down to the foundations in the ground. These beams and columns need to be put in strategic places for this to work properly. And it's also important that engineers choose the right materials for the job. Only the strongest building materials are used for the structural frame. In a multi-storey building like this one, we have used a combination of concrete and steel. Concrete is great at handling compression, but steel is better at dealing with tension. So in a big job like this one, we designed the frame to include concrete beams and columns that have been reinforced with steel bars. This gives us the best of both worlds. The framework on this building is almost finished, and thanks to all the engineering know-how that's gone into the design, this building should still be standing strong for a long time to come.
Hello there, Ted Petrie with another Scope and a Flash. It is great to be with me. But when it comes to colossal feats of engineering, Australia really holds its own against the rest of the world. From the architectural and engineering masterpiece that is the Sydney Opera House to the magnificent Snowy hydroelectric scheme where the almighty forces of nature are channeled to generate power. From the tiny electronic marvel that is the cochlear ear implant to the 3,000 kilometres of parallel steel that is the Adelaide-Darwin rail link. Wow, engineers have certainly made an impact on this country, but I think we both know who's made the bigger impact. I'm Ted Petrie, and I'm a national icon.
Yeah, perfect. Lovely. Well, my construction is starting to take shape, although clearly it still needs a door. I'm not very fast at this. Oh, unlike our next story, it's all about going fast. And then, just a little bit faster.
Machines really are all around us. Whether these machines are helping us travel from A to B, manufacturing thousands of items in a single day, or providing us with a thrilling ride, they all have one thing in common. They were all designed by mechanical engineers like us. Hi, I'm Lauren.
And I'm Tom, and we're part of a team of engineers about to test our skills on the racetrack.
Mechanical engineers work on just about any design project that involves some kind of movement. Cars are a great example, but we also work on projects like power generation or even climate control in new buildings. Movement is the name of the game, and in our current project, we're trying to make it as fast as possible. We're building a Formula SAE racing car to compete in a high-speed race at the end of the year. The competition isn't just about lap times though. The cars are also being judged on cost, energy efficiency and design practices. So when building a car like this, where does the process really start? We begin by looking at similar projects from the past and then come up with ways we can improve on existing designs. We then decide which parts we'll have custom made and which ones we'll buy off the shelf.
But before we can order any custom parts, we need to come up with some designs for the manufacturers to follow. In this project, the suspension system, chassis and bodywork were all designed from scratch. We use 3D modelling software to design each part individually and then use the same software to see how they would all fit together. We also need to check how these virtual parts would handle the forces applied when racing around the track. This takes some complex maths, so again, the computer comes in really handy. We may have to redesign parts many times before they can handle the forces produced by high-speed driving. Once the virtual parts have been given the all clear, we can order them in from a manufacturer. When the parts arrive, the most hands-on job begins. We assemble the car ourselves and it's a lot of fun, but not always smooth sailing. Sometimes we might find it difficult to get tools into the right spot, or parts might not fit together as well as planned. If this happens, we redesign the problem area and order in a few new parts. Once the car's assembled, it's time to start the engine and move on to testing. And the fine-tuning continues right up till race day.
But that's not for a few months yet. So for now, it's back to the drawing board as we try and find every advantage we can get.
Have you ever heard the expression, it's not rocket science? Well, how wrong they were, because coming up, that's exactly what it is. So far, all of the engineering stories that we've been checking out have been Earth-based. Not that that's that surprising, really. Yeah. But this next story, well, it propels things right out of this world.
A lot of people will tell you that what they do is not rocket science, but I won't. Rocket science is exactly what I do. Hi, I'm Mark. I'm an aerospace engineer, and this is what my team and I are working on right now. It's a liquid-fueled rocket motor. It can produce 2,500 newtons of thrust, and it's much like those already being used to propel space vehicles around the world.
And liftoff of Columbia with the Microgravity Science Laboratory.
So what are the various parts of this motor, and how does it work? Well, let me explain. This jar-shaped cylinder, which is open at one end, is the motor's combustion chamber, and it's connected to two fuel tanks. One of these tanks contains liquid oxygen, and the other contains kerosene. And it's when both of these liquids are injected into the combustion chamber and set alight that we get rocket motor liftoff. You see, once the liquids ignite in here, they turn into gases, and then they take up a lot more space. So a massive increase in pressure inside the cylinder results. The gases push very hard against the walls of the cylinder and rush out its open end, seeing the motor speeding off in the opposite direction. Now, building a rocket is one thing. Making it run efficiently, that's something else. And that's why we need a contraption like this. This is a test rig. Its job is to stop the rocket motor from speeding off into space when we test it, and to collect lots of information about its performance. Devices on the test rig measure the thrust and fuel consumption of the rocket motor, and the temperature and pressure inside its combustion chamber. By keeping an eye on these things and making the right adjustments, we've managed to work out exactly how to make our rocket fly with maximum efficiency. As our rocket flies through the atmosphere and gets faster than the speed of sound, we can make it even more efficient by combining the rocket with a ramjet. A ramjet is a device that can allow a rocket motor to capture the oxygen it needs for its combustion chamber directly from the air as it travels. And since a rocket motor that can capture its own oxygen doesn't have to be weighed down by lots of stored liquid oxygen, it can fly much faster than others. That's why rocket motors with ramjets will probably power the next generation of aircraft, space planes. Space planes will be used like regular planes, but they'll fly much higher and travel a lot faster. We rocket scientists have a bit to do between now and then, so I suppose I better get back to work.
Ah, yes, yep. That'll do nicely. You may have heard me mention before that I'm a chemist, and chemists make things in labs, right, using beakers and flasks and all of that. But what if you want to make chemicals on a big scale? Well, you get a chemical engineer.
Furnaces, reactors, boilers, compressors, valves and pipes. They're all important parts of this petrochemical plant. And making sure they're all in good working order is a big part of my job as a chemical engineer here. Hi, I'm Louise Laz and I'm going to show you what I do. But first, here's a bit about chemical engineering in general. Chemical engineering deals with the design, improvement and maintenance of equipment and plants that make useful or valuable products. Chemical engineers not only design equipment and plants, but they identify and correct faults in equipment and ensure that plants operate in a safe, efficient and eco-friendly way. So come and see what I get up to on a typical day. Usually I start out in the office. Here's where I check that the end product of our plant, ethylene gas, is being made at a rate that's up to speed. Today the system's telling me that our production is down a bit. And although it shows me where in the plant there might be a problem, to pinpoint the faulty piece or pieces of equipment, I'll need to make some further investigations. Here in our control room, operators have access to detailed live information that's coming in from all areas of the plant. So asking them if they've noticed anything unusual is the first thing I do. And today it seems there's been an unexpected rise in pressure in the pipes that feed into 2 of our heat exchangers. Heat exchangers are devices that transfer heat from one substance to another, and there are dozens of them here at our plant. Right now though, it's either heat exchanger number E701 or E702 that's the problem. So next I head to the plant to see what's going on. I take a thermal imaging camera and an infrared laser gun, and I use them to check the surface temperature of all of the pipes that connect to the 2 heat exchangers I'm investigating. And now I need to take the temperature data I've collected back to the office. I enter it into a spreadsheet, which does some calculations that let me identify which one of the heat exchangers is faulty. I then speak to our maintenance crew and ask them to take the problematic one out of the production line and give it a clean. Now, since your scope cameras aren't allowed near equipment that's been open for maintenance, for safety reasons, you won't be able to see it being cleaned. So come inside and wait with me. Well, that was maintenance saying that the exchange is clean now. And before it can go back to work, I need to inspect it. And it's safe for you to film now, so come take a look. After checking that its tubes are clean of the fouling that can build up in them over time, I give this heat exchanger the all clear and ask maintenance to reinstall it. It looks like cleaning that heat exchanger's done the trick. Our production rates are back up to normal, which means I should probably get back to another important but less glamorous part of my job, the paperwork.
Okay, settle down. Oh, well, that was engineering. And this is engineering. Oh, now if you missed anything on today's show, well, don't worry. You can just catch it on our website. And don't forget to join us next time when the ordinary becomes extraordinary. Kind of like my tower. Under the scope. That's why I'm not an engineer.